Hello, everybody. Welcome to Unit 1 through 4 overview. My name is Kelly. I will be taking you on this journey today. How are y'all doing today? How's quarantine life going? Ramping up for the exam? Super fun times? All right. Okay, so let's go ahead and get started. So like I said, we're doing Unit 1 through 4 overview today. This is going to be less of problem solving because that's what the 1 o'clock stream with Peter has been focusing on, is the free response questions that your exam is going to be made up of. Today we're really just going to go over what College Board deems the essential knowledge for each of these units. So it's going to be a lot more content and a lot less problem solving, but there are going to be a couple problems peppered in there just to kind of get your gears turning. All right. So as always, you can find us on Twitter, Instagram, or YouTube, and we also now apparently have a TikTok, so go check it out, I guess. See what fun things are on there. Okay, so the 4 units that we're going to cover. Unit 1 is kinematics. That's all of our constant acceleration motion equations and whatnot. Unit 2 is dynamics. That's getting into our forces and what causes the motion. Then Unit 3 is circular motion and gravitation. And Unit 4, we're going to finish up with energy. All right. So to get started, Unit 1, kinematics. The 2 main topics that are included in this are position, velocity, acceleration, and then representations of motion. So to begin with our position, velocity, and acceleration, things that you need to know. An observer in a reference frame can describe the motion of an object using quantities like position, displacement, distance, velocity, speed, and acceleration. So these are the six things that we use to describe the motion of an object. And it's always important to focus on the same reference frame. Displacement, velocity, and acceleration are all vector quantities, while distance and speed are not. So that's one of the things that students get mixed up with a lot, is distance and displacement in particular, because displacement is just how far are you from where you started, whereas distance is like how far did you actually go, like back and forth. All right. And with all of these things comes a plethora of equations. So displacement, like we said, is your change in position. So it's where did you end minus where did you start. So if you go on a big long journey, it's literally just like the bird's eye view from where did you start to where you ended. And that's a vector, so that has a direction and a magnitude. And we write that as delta x, which is the change in position. Right? So velocity is the rate of change of the position with time. So that's your displacement if you're using your average velocity. So it's delta x over delta t. Likewise, your average acceleration is the rate of change of the velocity with time. Now, if y'all end up taking physics C in the future, which maybe you might, if you decide to take 3 years of AP physics, I don't know your life, but when you get to college physics anyway, you're going to learn the derivative values of these as well. But that's for another time. Okay, so changes in each property are expressed by subtracting initial values from final values. So anytime you see that nice delta sign, it just means final minus initial. All right. The choice of your reference frame determines what direction and magnitude each of those quantities have. So there's a couple of situations where we're not going to use the typical XY coordinate system that we're used to using. So you're probably familiar with the block sliding down the ramp. and how it makes it a lot easier to take your XY axes and rotate them to be along the ramp, right? So that's you choosing your reference frame to decide the direction and magnitude. You also might encounter a situation where you're on a train going at a constant speed, or a constant velocity, excuse me. And so your reference frame is the reference frame that's on that versus the reference frame if you were standing on the side of the train track. All right. Now, there are 3 fundamental interactions or forces in nature. We're used to saying there's 4, but electromagnetism and the weak force have been since unified so beautifully. All right, so those are the gravitational force, the electroweak force, and the strong force. And those fundamental forces determine the structure of objects and the motion of objects. So on your AP exam, you will be expected to know what those fundamental forces are. Okay. All right. So now this one's a lot, sorry. All right, so in inertial reference frames, forces are detected by their influence on the motion, specifically the velocity of an object. Force, like velocity, is a vector. And a force vector, since it's a vector, means it has a magnitude and a direction. And when you have more than one force on the object, if you add up all those forces, you take the vector sum, that's the net force. And that net force causes a change in the motion of the object. And the acceleration of the object is proportional to that net force. So that's just a very long-winded way of saying the sum of the forces equals ma. Now, the important thing to remember with Newton's second law, which is our F equals ma, is that it's in an inertial reference frame. So, in the chat box, what does that mean? Like, what does it mean to be in an inertial reference frame? Feel free to type a little something. We'll give you a minute. Yeah, a minute sounds good. Maybe we'll get a surprise visit from a cat in the meantime. I don't know. Good, 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 good. Awesome. Awesome. Yeah, so if you're in an inertial reference frame, that means you're going at a constant velocity. We're used to seeing that velocity equal to 0. It doesn't accelerate. There's no net force acting on it. So there could be something acting on it, but it needs to all cancel out. So if, say, we're on a train car that's accelerating, this would not be an inertial reference frame because that acceleration is going to cause that pendulum to tilt. So we're like, yes, something fishy is going on here. We must be accelerating. Yep. So Newton's second law only works in an inertial reference frame. That's when acceleration is equal to 0, no net force, velocity is 0, or velocity is constant, excuse me. Good job, team. All right. Sweet, so our kinematic equations only apply to constant acceleration situations. And again, this is something that you're going to really dive deep into once you get to calc-based physics. So the kinematic equations that you know and love are Vx equals V naught plus AT, x is x naught plus Vt plus 1/2 AT squared, or V final squared is V initial squared minus 2a delta x. Woo! Only apply constant acceleration. And circular motion and projectile motion both count for constant acceleration. So if you're going in a circle at a constant velocity, that is a constant acceleration, pulling you towards the center, that counts. And your projectile motion, gravity, that counts. All right, and you can use these in both the x and y direction, which if you've done your projectile motion equations, you are very familiar with. All right, so that was the first chunk of Unit 1. The second chunk is representations of motion. So the linear motion of a system can be described by the displacement, the velocity, the acceleration of its center of mass. So whenever we're talking about like this object has this acceleration, we're talking about the center of mass of that object. So you could very well do it as like the clump of particles in a cloud of something, galaxy stuff. I don't know, I'm spitballing here. But it's always with the center of mass. So if you have, if you have like 6 particles that are all tied together, all of those linear motion equations apply to the center of mass of those 6 particles. Right, and the acceleration of the center of mass of that system is directly proportional to the net force exerted on it by all the objects interacting with the system and inversely proportional to the mass of the system. In other words, sum of the forces equals ma. All right. Sorry, I'm giving you the essential knowledge bits direct from College Board, which is why they probably sound extremely wordy. Okay, so force and acceleration are both vectors, and the acceleration is always in the same direction as the net force, which makes sense, right? If I push on the box is going to accelerate in the same direction that I'm pushing on the box. And again, the variables x, your position, v, your velocity, and a, your acceleration, are all referring to the center of mass quantities. All right. Now, this is one of our nice throwing out a question every now and then. So the graph above shows the velocity versus time for an object moving in a straight line. At what time after t equals 0 does the object again pass through its initial position? Go ahead and throw an A, B, C, or D in the chat box when you are ready. All right, let's give you about 20 more seconds. We have a guest appearance maybe soon. All righty. All right, so if we come back to the initial position, that tells us that our displacement is going to be 0. So now when we're looking at a velocity time graph, how do we get displacement out of that? Right, it's the area under the curve. So the red area under this curve is our displacement away from our initial position because it's under that time axis. So in order to get back to where we started, we need to cancel it out with a positive displacement. So that's going to happen sometime between 1 and 2 seconds. So our answer is B. Now this was a tricky one because you see it and you're like, oh, okay, I get back to 0 at 1 second, right? You're like, But alas, or between 2 and 3 seconds when your velocity is constant, that can also trick you up too. So between 2 and 3 seconds, when we have that slope is 0, that's when our acceleration is equal to 0, but we're caring about the displacement, which is our area under the curve. All right. So it's like have you guys ever seen that like tree, if you will, where it's like acceleration, velocity, displacement, and to go up the tree, you take the area under the curve, and to go down the tree, you take the slope? I'll post it. I'll post it in the resources on this back on Fiveable, so you can look at it later, because I don't have it right now. But yeah, so if you want to go up the tree, you want to take the area under the curve. So to get from velocity to displacement, it's the area under the curve. And if it's below 0, it's negative, and if it's above 0, it's positive. And if we want to go down the tree, we take the slope. All right. Okay, so that's the end of Unit 1. Next up is Unit 2, which is dynamics. That covers your systems, gravitational field, contact forces, Newton's first, second, and third law, plus free body diagrams, and then applications of Newton's second law. Woo, that's a lot. All right, so systems. So a system is just an object or a collection of objects. And when we're talking about objects, we treat them as if they have no internal structure. So when we say like the ball rolls down the hill, we don't care what's happening to like the molecules inside the ball. We're just saying the ball is an object. We don't care about the internal structure at all. And a collection of particles in which internal interactions are changing little or not at all, or in which these changes in these interactions are irrelevant to the questions addressed, can be treated as an object. So this is if we're talking like about a system of particles again. So those internal interactions, if they're like crashing into each other, jiggling around a little bit, if it's not relevant to the question addressed, we don't care. We can treat the whole collection as an object. All right. Some elementary particles are fundamental particles like electrons. And then sometimes you get protons and neutrons, which are composed of those fundamental particles like quarks. And depending on the type of problem, they can either be treated as a system or as an object. So sometimes they'll be like, the proton is traveling at whatever speed. What is the distance of the proton? We're treating that proton as an object. We don't care about the quarks inside. But then sometimes they're going to be like the hydrogen atom. They like to use a lot for circular motion. So they use the Bohr model of the atom where there's the proton with the electron orbiting it like a planet. They use that a lot as a system instead of just like the entire object of the hydrogen atom. So it depends on the context of the problem. All right. Systems have properties that are determined by the properties and interactions of their constituent atomic and molecular substructures. So what that means is that in AP Physics 1, when the properties of the individual parts are not important for modeling the behavior of the entire system, you can just refer to the system as an object. So like our protons. The quarks are irrelevant for all of the problems in Physics 1, so we treat the proton as an individual object instead of a system of quarks. Does that make sense? Alrighty. Next up in Unit 2 is the gravitational field. Gravitational field, you don't get it. Okay. Cool. Thank you for telling me. Okay, so yeah. So let's say, yeah, we're going to keep using the proton example. So we have our proton, right? And our protons are made of 3 quarks. I think it's like what, up, down? So instead of being like, okay, I have 3 quarks, I need to look at how each of those quarks is moving individually in order to solve a problem that asks about the speed of a proton. Well, we don't care about what the quarks are doing. We care about what the proton is doing. So when you're looking at a problem, you want to identify the system that's going to allow you to solve, like to do what they're asking, basically. So So let's say in the example of this hydrogen atom that's on the screen right now, if the problem was like there is a hydrogen atom traveling at a speed of 3 times 10 to the 4 meters per second. Yeah, that sounds like a reasonable number. How far does it travel in a second? Okay, well, we don't care. We don't care that the hydrogen atom has a proton and an electron. We don't care because we ask about the whole hydrogen atom. So we can treat that hydrogen atom as an object by itself. Just say the hydrogen atom is moving. How far did it move? The end. So that's our system. However, if the problem is like, here's a hydrogen atom, there's a proton, there's an electron. The electron is moving around the proton. What's the speed of the electron? Then we care about the individual pieces. So we care about the proton, we care about the electron. So even though both problems have a hydrogen atom, depending what the problem is asking is, are you going to look at it as a proton electron, or are you going to look at it as a hydrogen atom? Does that help? Does that make more sense? Cool. All right. Okay. Unit 2, gravitational field. All right, so a gravitational field is little g, and at the location of an object with mass m causes a gravitational force of magnitude mg to be exerted on the object in the direction of the field. Which, on Earth, this gravitational force is called weight. So this is our familiar F equals mg, right? So the force of gravity by some massive body is the mass of the thing that's in the field, so like the apple falling, times g, the gravitational field. All right. So on Earth, what direction does the gravitational field point? Feel free to throw that. Okay, down, towards the center. Yeah. So if we're just zoomed in really close to the surface, so like I'm standing on the ground, I have an apple and I drop it, you're right, it points down. But if we zoom out and we look at the Earth, it points towards the center. So all of you are technically correct. So it depends if you're looking at the surface or if you're looking at the planet as a whole. So again, this comes into context of the problem. All right, so similarly, you can find the gravitational field at any point in space by looking at the force and dividing it by the mass of some test object at that point. So in other words, you can take F equals mg and just rearrange the equation. So g is your gravitational field. You can measure the force and divide it by the mass of the object that you're measuring the force on. Yeah. All right. So if the gravitational force is the only force exerted on the object, the observed free fall acceleration of the object in meters per second squared, those are our units of acceleration, is numerically equal to the magnitude of the gravitational field in newtons per kilogram at that location. So, in other words, the acceleration of something that is just falling to its peril is equal to the gravitational field, the magnitude of the gravitational field. And the direction of that is going to be towards the center or down, depending if you're zoomed in or zoomed out. Cool, cool. Now, the cool part about this is that it applies to all planets. Everything applies to anything that has mass and a gravitational field associated with it. So we're used to seeing it on Earth of g is 9.8 meters per second squared, but you can also apply that to the moon, Mars, the sun, anything. An entire galaxy if you want, which we're going to get more into in unit 3. Yeah, 3. All right. Next up is contact forces. So our contact forces, as it sounds, result from the interaction of one object by touching another object. And they arise from interatomic electric forces. And these forces include tension, friction, normal, and spring. So tension you're familiar with. That's if you're like hanging on a string, the string pulling you back up has some tension in it. You're pulling it really tight. Friction is when you're like floating along, where the magnitude of your friction force is less than or equal to mu times the magnitude of your normal force, where mu is your coefficient of either static or kinetic friction, depending if you're chilling or if you're moving. Normal force is like if you're sitting on a table, the normal force is the thing that's pushing back up on you, keeping you from falling down to the ground. And your spring force. Oh yeah, I'll answer that later. I'm going to add that to the question box. Cool. All right. Where was I? Okay, so the spring force, the magnitude is equal to kx. Now, you're probably used to seeing this as spring force is negative kx. So again, this depends on what your reference frame is, what you define as being 0, if you're displaced to the right, to the left. Your spring force is always going to be a restoring force. So if you take, let's say you have a spring with a block on the end, and you stretch it out, your spring force is going to be trying to pull it back in. If you smush it in, your spring force is going to be trying to push it back out. So it's always helpful to look at what is going on instead of just blindly putting in pluses and minus signs, because that will be your downfall. Trust me, that was my downfall when I took physics, was just saying, oh, well, there's a minus sign in the equation. So you always want to just think about what's actually going on. Okay? All right. Next up is Newton's first law, which tells us that the inertial mass is the property of an object or a system that determines how its motion changes when it interacts with other objects or systems. So basically what you need to get out of this is that your inertial mass does not change, ever. It is an intrinsic property of that matter. So whether you are on Earth, whether you are on the moon, whether you are floating through space in a vacuum, your mass is always the same. And my favorite thing to show, if I can get back to my thing. Where'd you go? There you are. Play.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
How about that? So, just as our Newton's second law tells us, sum of the forces equals ma. If you're on the moon, our acceleration is the gravitational pull of the moon. And the mass doesn't matter as far as if it's going to accelerate or not. They're going to accelerate at the same rate, which is neat. Sorry, I like that video. It's a fun video. All right. Newton's third law in free body diagrams. Forces are described by vectors. Forces are detected by their influence on the motion of an object. And forces have magnitude and direction because they are vectors. So that seems pretty straightforward, but for some reason they just put it in their essential knowledge checklist like 18 times. So I'm going to tell it to you like 18 times. Forces are vectors. Alrighty. A force exerted on an object is always due to the interaction of that object with another object. In order to have a force, you have to have something providing that force. It's not just going to magically appear, is what that's saying. An object cannot exert a force on itself, which makes sense. And even though an object is at rest, there may be forces exerted on it by other objects. So, like our box on a table, we have gravity, we have normal force. So, even if it's at rest, there's probably still forces acting on it. They just cancel each other out. The acceleration of an object, but not necessarily its velocity, is always in the direction of the net force, because F equals ma. So whatever way you push is which way your acceleration is going to go, but not necessarily the velocity. So think of it like I'm trying to slow something down from falling on my head. I'm pushing up, and my acceleration is up because I'm slowing it down, even though the box is still trying to crush me to my death. That was morbid, sorry. Anyways, if one object exerts a force on a second object, that second object is always going to exert a force of equal magnitude on the first object in the opposite direction. Or as you are probably more familiar, for every action, there's an equal and opposite reaction. If I push on you, you push back on me the same amount. In Newton's second law, if an object of interest interacts with several other objects, then the net force is just the vector sum of the individual forces. So our sum of the forces is just F1 plus F2 plus F3 plus blah, 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 blah. And remember, you always want to add up the individual components, so all your X components, all your Y components, not just add them all up. So it's a vector sum, not just a magnitude sum. Okay. Free body diagrams are useful tools for visualizing forces being exerted on a single object, and therefore writing the equations that represent a physical situation. So an object can be drawn as if it were extracted from its environment, and the interactions with the environment are identified. In other words, a force exerted on an object can be represented as an arrow, whose length represents the magnitude of the force, and whose direction shows the direction of the force. So in the example of this block of cheese sitting on a table, the weight is pulling it down, the normal force from the table is pushing it up. They are equal magnitude because acceleration is 0, so the lengths of those are the same. So hopefully you've drawn your fair share of free body diagrams in your physics class, because you will be expected to draw free body diagrams on your exam. Okay. Now the coordinate system with one axis parallel to the direction of the acceleration simplifies the translation from a free body diagram to the algebraic representation. So this is why whenever we have the block sliding down the ramp, we pretty much always rewrite our coordinate system so that x is pointing along the ramp and y is coming out perpendicular to it. It just makes the problem a heck of a lot easier if your acceleration is in the same direction as one of your coordinate axes. All right. Free body or force diagrams can be depicted in two ways. First is when the forces on an object are represented as arrows pointing outward from a dot. So like on our left, we just draw the dot and then draw forces off of that. Or you can have the object and then draw your forces specifically where they're interacting with the box. So for our box, our normal force is acting at the bottom surface, pushing up. Our gravitational force, mg, is acting at the center of mass, and our contact force is at the side. So this is a personal preference of whether you prefer the dot or the object. Personally, I do some combination of the two just because I like drawing blocks. So instead of drawing a dot, I draw a block. Like over here. See how they have the block It has the forces from a dot in the center. That's how I draw it. So it's up to you, personal preference. But those are the two ways that you draw free body diagrams. All right, then we get into our applications of Newton's second law. Oh, is it? What question? Oh, yeah. Yep, you're right. Yep, so our y would be alpha cosine. Good thing I'm not answering that question. Oh, that's a good point, though. Whenever you rotate your coordinate axes like that, make sure that your angles end up in the right place, because sometimes it'll get funky. So don't just blindly trust the equation sheet that it's f cosine theta or f sine theta. Always double check, because sometimes they'll move the angles just to trick you. I've seen it. I've fallen for it. Don't do it. All right, where were we? This one. Okay. So forces that the system exert on each other are due to interactions between objects in the systems. If the interacting objects are part of the same system, there will be no change in the center of mass velocity of that system. So that goes back to like our proton electron example. So since we said that our system is the proton and the electron, the center of mass is not going to, velocity is not going to change because we're looking at it individually. Okay. And that's like the walking on a boat example that you might have done with conservation of momentum. So if I have my boat on the water and me on the boat, if I walk this way, my boat is going to move to compensate the center of mass so that the center of mass doesn't move. Okay, so now we're hopping back in with another question. So we have a 2 kilogram block sliding down a 30-degree incline as shown above with an acceleration of 2 meters per second. Which of the following diagrams best represents the gravitational force W, the frictional force little f, and the normal force N that act on the block? Sweet. Good job, team. Great. So our answer is D. And a way we can tell that is because your weight should always be pulling straight down, like we said earlier, so that immediately knocks out A and C. And your normal force always comes out normal to the surface that you're on. So because we're on a ramp, our normal force is going to be crooked. So that knocks out B. And then our frictional force always wants to go in the opposite direction of motion. So if we're sliding down the ramp, our frictional force is going to be going the opposite way. Good job. All right, unit 3, circular motion and gravitation. This covers vector fields, our fundamental forces again, gravitational forces, gravitational field, and acceleration due to gravity on different planets. And then also inertial versus gravitational mass, centripetal acceleration and centripetal force, and free body diagrams for objects in uniform circular motion. Woo! So there's a lot in Unit 3, but it doesn't make up much of the test. I think it's like 4 to 6%. It's really small. Basically, all you need to remember is that your vector field gives as a function of position and sometimes time, but I would be very surprised if you get a time-dependent field on AP Physics 1. But it tells you the value of that physical quantity, and it's described by a vector. So vector fields are represented by field vectors indicating direction and magnitude. So going back to our Earth picture from earlier, how all the arrows were pointing towards the center, that's a vector field. And it's drawn by field vectors indicating the direction. And when more than one source object with mass is present, the field value can be determined by vector addition. So just like with forces, you find the total force by adding them all together. You find the total field by adding them all together. And conversely, if you know the field, you can use it to make inferences about the number relative size, and location of the sources that create that field. So if I tell you that gravity is 9.8 meters per second, you can be like, yes, I deduce that that is probably from the Earth because it has the mass and the radius that gives that up. So from our fundamental forces aspect, we already talked about the three fundamental forces. In particular, gravitational force is exerted at all scales, both subatomic and universal size, huge, and it dominates at the largest distances and mass scales. So unlike our electroweak and our strong forces, which really only work when you're really close, really small things, like your strong force, I think the range is like something like, what is it, 10 to the negative 10 meters? Don't quote me on that. I'm just pulling it out of my brain. Gravity goes kilometers, light years, huge range, but it's very weak compared to the other ones. But because the other ones are short range, gravity takes over at large distances. Okay, so gravitational force describes the interaction of one object with mass with another object that has mass. And your gravitational force is always attractive. So that field is always pointing to the center. It's never pointing outward. Unlike for electricity. Okay, and the magnitude of that force between your two spherically symmetric objects of mass m1 and m2 is g m1 m2 over r squared, where r is the center to center distance between the objects, not surface to surface, center to center. That's a place where people get tricked up. And in a narrow range of heights above Earth's surface, so when you zoom in on the surface, the local gravitational field G is approximately constant. So that's why we can use G equals 9.8. But once you get far away from the surface, then you have to go back and use GMM over R squared because it starts getting less than 9.8. All right, so the gravitational field at any point in space is measured by dividing the force exerted by the field, so our GMM over R squared, by the mass of the test object. And if the gravitational force is the only force on the object, again, the free fall acceleration is going to be equal to the magnitude of the field. So you can calculate what G is on all the different planets by dividing the force by the mass. All right. So the gravitational field is G m source, so that's the planet, over R squared from where you're measuring it. So at the surface of the Earth, where R is the radius of the Earth, you get the 9.8 meters per second squared. And all of these equations are on your equation sheet, so don't worry, you'll be fine. Okay. Gravitational mass is a property of an object or a system that determines the strength of the gravitational interaction with other objects, systems, or gravitational fields. The gravitational mass of an object determines the amount of force exerted on the object by a gravitational field. Woo! Okay, so basically what that's saying is if we can measure the gravitational force on an object, we can determine the mass of whatever object made that field in the first place. And we call that its gravitational mass. But the cool thing about that is that it's just the same as the inertial mass. All of the experiments that we've ever done, we cannot get a difference between the inertial mass, so just pushing on it with regular forces, and the gravitational mass, so just using gravity as it. They're the same. It's just how you measure it determines what you call it. It's weird. But just know that they're the same. Your mass is your mass is your mass, whether it's inertial or gravitational. It's the same. All right. So near Earth's surface, all objects fall in a vacuum with the same acceleration, regardless of their inertial mass. This goes back to our guy on the moon dropping the hammer and the feather. He's in a vacuum, mostly, because the moon doesn't have an atmosphere. So they fall with the same acceleration, even though the hammer is definitely heavier than the feather. All right. Objects and systems have properties of inertial mass and gravitational mass that are experimentally verified to be the same and that satisfy conservation principles. So this goes back to the inertial mass is the gravitational mass. They're the same. Mass is mass is mass is mass. Woo. All right. Then we get into our centripetal acceleration and our force. So for rotational motion, there's analog quantities such as angular position, angular velocity, and angular acceleration. We're going to talk more about that next week in Unit 7 because that's where we really drill down on circular motion. But this also includes situations where there's both a radial and tangential acceleration for an object moving in a circular path. So we threw this into Unit 3 because your centripetal acceleration gives you those nice circular orbits, which are almost, I won't say almost always, but can be applied to circular orbits of planets because of gravitational fields. So they like to talk about those two things at the same time. All right, so your centripetal acceleration, AC, is v squared over r, where v is your tangential velocity, so it's how fast you're traveling around in the circle, divided by r, which is the radius of the circular path that you're traveling in. And that centripetal acceleration always points to the center of the circle, always. All right, so given a radius r and a period of rotation t, you can calculate the velocity around your circle by 2 pi r, so that's your distance around a circle, divided by the time it takes to get around the circle t. So it's distance over time, but specifically in a circle over the specific time period. Okay. Da-da-da. Switch. Okay. Here we have another practice problem. So the horizontal turntable shown above rotates at a constant rate. As viewed from above, a coin on the turntable moves counterclockwise in a circle as shown. Which of the following vectors best represents the direction of the frictional force exerted on the coin by the turntable when the coin is in the position shown? Trying to get you a guest appearance by the cat. Jeannie, come here. Psst, psst, psst. While you answer. 3. Okay. Oh, there's 3. Okay, sweet. Right, good job. So when we're talking about circular motion, I like to think of it as what is keeping the thing in a circular path? What is keeping it from flying off into space? That is your centripetal force. So in this case, the thing keeping our coin on the disc is the friction, and your centripetal force always points to the center. So it's C. Good. Okay, so then we get into free body diagrams for objects in uniform circular motion. So our free body diagrams are useful tools for visualizing forces being exerted on a single object and writing the equations. So we said that already. So you can use free body diagrams for circles as well. Just remember that your centripetal acceleration is always going to be pointing towards the center of whatever that circle is. And then you can draw your free body diagrams as you normally would. So like the loop-de-loop example, your free body diagram at the bottom and at the top are going to be different depending on which way is towards the center. All right. And now we go into Unit 4, energy. This is open and closed systems, energy, work and mechanical energy, and then conservation of energy, the work energy principle, and power. So for open and closed systems, energy. So again, a system is an object or a collection of objects. And the objects are treated as having no internal structure. You get to define what the system is. So for all systems, under all circumstances, energy, charge, linear momentum, and angular momentum are conserved. For an isolated or closed system, conserved quantities are constant. So that's like have y'all seen the like spinning the bicycle wheel while sitting on the little stool and you're like just chilling and then you flip it over and then you start spinning the other way? That's because your angular momentum, like the closed system that is you on the stool with the bicycle, your angular momentum is conserved and constant. So an open system is one, they made you do that in class. I love that one. It's fun. You can go crazy. But yeah, so an open system is one that exchanges a conserved quantity with its surroundings. So with that same example, that would be like, if the system is you on the stool with the bicycle wheel, that would be like if your friend comes over and pushes you. That is an external thing giving stuff to your system. So that is not going to be conserved. Well, it's still conserved, but it's not going to be constant anymore. Cool. All right. So an interaction can be either a force exerted by objects outside the system, so like your friend pushes you, or a transfer of some quantity with objects outside of the system. So that's like you decide to throw the wheel away. You change your system. The placement of a boundary between a system and its environment is a decision made by you, the person, considering the situation in order to simplify or otherwise assist in analysis. So if you want to do a conservation of energy thing, it makes it a lot easier if your energy is constant, right? So you choose your system so that anything that's exchanging energy is in your system. Or otherwise, you have outside work. So it's up to you. You get to define your system. All right. The change in kinetic energy of an object depends on the force exerted on the object and on the displacement of the object during the interval that the force is exerted. Only the component of the net force exerted on an object parallel or anti-parallel to the displacement of the object will increase parallel or decrease anti-parallel the kinetic energy of the object. And the magnitude of the change in the kinetic energy is the product of the magnitude of the displacement and the magnitude of the component of force parallel or anti-parallel to the displacement. In other words, your work is equal to your change in energy, which is the parallel component of the force to the displacement. So sometimes you'll see this as FD cosine theta, I think is how they have it on your equation sheet. It's not always cosine. Sometimes it's sine. It depends. It's the parallel component of the force with your displacement. So if you are pushing in the same direction as your movement, you're increasing the energy. And if you are pushing in the opposite direction of your movement, you are decreasing the energy. And if you are pushing perpendicular to the movement, nothing's happening. No work. There's no work done. Okay. The component of the net force exerted on an object perpendicular to the direction of the displacement of the object can change the direction of the motion of the object without changing the kinetic energy of the object. So the most, we'll say the most important example of this is your uniform circular motion. So if I have a planet and a moon orbiting it, my velocity and therefore my displacement is always going to be tangential to that circular orbit, right? But my force is going to be pulling me inwards. So my displacement and my force are perpendicular. So gravitational orbits and circular motion do no work because the force is perpendicular to your displacement. That is a group favorite. We'll say a College Board favorite for conceptual questions on an exam. Granted, you don't have multiple choice, so I'm not sure how it's going to work. Maybe you'll get a circular orbit for your response. We'll find out. All right. Kinetic energy. Your translational kinetic energy is 1/2 mv squared. Your rotational kinetic energy is 1/2 I omega squared. We're going to talk about this a little bit more next week with rotational motion again. And it can be a combination of both. So if you have like a ball rolling down the ramp, it's rotating, so it has rotational kinetic energy, but the center of mass is also moving, so it also has translational energy. So a rotating rigid body may be considered to be a system and can have both translational and rotational kinetic energy. So that's why you always want to look at the center of mass. Is the center of mass moving? Yes, translational. Am I rotating? Yes, rotational. Sometimes there's both. Okay. The energy of a system includes its kinetic energy, potential energy, and microscopic internal energy. So this includes gravitational potential energy, which is our negative g m1 m2 over r, or close to the surface, mg delta y. Our elastic potential energy, which is our 1/2 kx squared if we have a spring, and our kinetic energy, our 1/2 mv squared, or 1/2 I omega squared. Okay, so although thermodynamics is not part of Physics 1, it's in Physics 2, we do include the idea that during an inelastic collision, some of the mechanical energy dissipates as thermal energy. So when you're talking about like conservation of momentum, when you have your inelastic collision, like your two cars smush and then they stick together, some of that energy is lost due to thermal energy of the collision. They don't need you to calculate it, they just need you to understand that concept. Okay. Mechanical energy, which is the sum of your kinetic and potential energy, is transferred into or out of the system when an external force is applied on the system, such that a component of the force is parallel to its displacement. In other words, if you do work, you change the energy. So if the force is constant, then the work done is the product of the displacement and the parallel component of the force. So again, that's work is FD, but F dot D, parallel component. Check your angles. And your work, your change in energy, can be found from the area under a graph of the magnitude of the force component parallel to the displacement versus the displacement. So if you have an FD graph, your work is the area underneath. Okay? All right. All right. Quick question. A 2-kilogram ball is attached to a 0.8 meter string and whirled in a horizontal circle at a constant speed of 6 meters per second. The work done on the ball during each revolution is... We're almost done, I swear. All right. Sweet. So which direction is the force in this case? If we're spinning around in a circle. Right, perpendicular to the motion. So we're spinning around in a circle. Our force is towards the center of the circle. Those two things are perpendicular, so there's no work. Good. Good job, team. All right. Classically, an object can only have kinetic energy since potential energy requires an interaction between two or more objects. So if you are an object floating in the void, we'll say, you can only have kinetic energy. Because potential energy, if you have gravitational potential energy, you need some object creating that gravitational field. If you have elastic, you need some spring. You need something. There's some interaction between two or more objects that has to exist in order to have potential energy. Is all that's saying. Okay. And a system with internal structure can have internal energy, and changes in a system's internal structure can result in changes in internal energy. So this is talking about our mass spring oscillators and our simple pendulums. So if we have a mass on the end of a spring and you pull it and it goes ding, 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 the period that it oscillates is 2 pi square root of m over k, where k is the spring constant. And if you have a pendulum with the mass on the end, it goes ding, 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 ding. The period of oscillation is 2 pi square root of L over G. And if you don't remember those, and if they're not on your equation sheet, which I think they are, you can calculate them from conservation of energy. All right. We have a couple more. We're almost done. A system with internal structure can have potential energy. Potential energy exists within the system if the objects within that system interact with conservative forces. Work done by a conservative force is independent of the path taken. And the work description is used for forces external to the system, and potential energy is used when the forces are internal actions between parts of the system. So basically what they want you to know is, what does it mean to be a conservative force? That means that the work done doesn't matter on the path taken. So the energy that you give or take away doesn't matter how far you go. So an example of that is gravity. If you lift it up, you're going to have the same gain in potential energy if I lift it straight up versus if I lift it up like this. Whereas friction, if you push it along, because you're losing energy in the form of heat with friction, the further you push it, the more energy it's going to lose. So a straight path to somewhere with a friction is going to lose less energy than a swervy path. All right. Changes in the internal structure can result in changes in the potential energy. So again, that's your spring oscillators and your objects falling. So if you change those things, your potential energy changes. All right. And the internal energy of a system includes the kinetic energy of the objects that make up the system and the potential energy of whatever objects are making up the system. So your total energy is your kinetic plus all your different potentials. And since energy is constant in a closed system, any changes in system's potential energy result in changes to kinetic energy. So in your closed system, your total energy is conserved. And the changes in potential and kinetic energies in the system may be further constrained by the construction of the system. So that's, again, if you're looking at the whole system versus if you're looking at one thing and you're doing an external something. All right? And last but not least, energy can be transferred by an external force exerted on an object or system that moves the object or system through a distance that's doing work. And your energy transfer in mechanical systems can occur at different rates. So you can do it fast, you can do it slow. And we call that power. So power is defined as the rate of energy transfer into, out of, or within a system. And that's your energy change divided by time. Okay, so to answer your question, how do you get more practice with your free response questions? Every Thursday at 1 p.m., same place, Peter does free response question streams, goes through all of the past free response questions. If you Google free response questions from AP Physics, you can find tons of previous year's exams and the scoring rubrics. You can also try looking up AP Physics B, because that's what it used to be called before they switched it to Physics 1 and Physics 2. And those free response questions are going to be very similar. And yeah, and I think there are resources on the Fiveable website, but I'm not sure. I don't remember. Okay, and then to round it all off, sorry I went 3 minutes over, we have another question for you. This one takes a little bit longer, so don't feel like you have to do it. Thanks for tuning in. Good luck on your exam. I'll be here next week with units 5, 6, and 7 review. And yeah, see y'all later. Thanks for tuning in. Hey! Sorry, my cats are fighting. Good. It does not be. You tried. No. But yeah, so we can look at it. So we have a pendulum consisting of a ball of mass m suspended at the end of a massless chord. Okay, I'll let you work it out. I'll stay here until you work it out. How about that? Meanwhile, I'm going to yell at my cats just a second. Hey, stop. Come here. It is A, yep. You're right. Ta-da! Good job. Yep. That 1/2 L is going to get you. That what L cos theta. L minus L cos theta is your change in height. Those ones are always fun. Those always get me because I'm just like, wait, what's the cosine of 60 again? Because I never memorized that. Cool. All right. Signing off. Have a good night. See you next week. Hopefully that was helpful. And don't forget to tune in to Peter with his free response review at 1 on Thursdays. See ya.